In this tutorial, we are going to discuss nuclear reactions and specifically the types of decay reactions that can happen to the nucleus of radioactive isotopes. Okay, so the first thing we'll talk about is the difference between chemical reactions and nuclear reactions. Then we will talk about the types of decay. There are three. And then we will talk about how to write and balance a nuclear equation. So the difference between a chemical reaction and a nuclear reaction is that chemical reactions involve the rearrangement of electrons. So when you have a chemical reaction, the electrons are the only thing that's really involved in bonds breaking and bonds forming. Whereas nuclear reactions are the rearrangement or the breaking down of the nucleus of the atom, which is made of protons and neutrons. And you'll remember that the nucleus is held together by the strongest force that there is, the strong nuclear force. So the short and skinny of it is that nuclear reactions will actually release way more energy than a chemical reaction ever will. I mean, it's tremendous amounts of energy. So this explosion that I have a picture of, this is a nuclear explosion. Splitting an atom releases massive amounts of energy because you're separating the protons from the neutrons. You're breaking that strong nuclear force. Okay, so let's talk about the types of decay. First of all, if you'll remember, radioactive decay from the last video is when you have unstable nuclei. Certain isotopes are very unstable and they break down over time to try to become more stable. So in the process, they emit particles or little chunks of the nucleus, as well as sometimes some energy. And remember that all elements are trying to get a proton to neutron ratio that is ideal for that particular element. So remember, the lighter elements want a 1-to-1 ratio, and the heavier elements are a little bit more of like a 1 proton to a couple of neutron ratio, if you remember from the band of stability that I showed you in the last video. It should be mentioned that this woman, Marie Curie, is the person that we credit for discovering that certain nuclei will actually emit radiation, which is invisible, by the way, over time. And they actually figured out how to use this radiation to do things like X-rays, and there's a lot of medical techniques that are used or that use this decay that Marie Curie discovered. So I just wanted to mention her right here. She actually won 2 Nobel Prizes. She was the first person to ever win 2 and the first woman or the only woman to ever win 2. Okay, so let's talk about the types of radioactive decay. All right, alpha decay is the first type of decay we're going to talk about. During alpha decay, an atom's nucleus actually spits out 2 protons and 2 neutrons as a little particle or bundle. And that bundle is called an alpha particle. So here's an alpha particle. So here's the nucleus. It spits out this little alpha particle. And then, of course, the nucleus now is 2 protons and 2 neutrons short of particles, and it changes its identity because you're losing protons, right? And I just want to mention that this little Greek symbol that looks like a fish is an alpha. So a lot of times you'll see alpha particles written like this, so people will actually write alpha particle. But the best known abbreviation for an alpha particle is this. So remember, we learned element shorthand. If you think about it, it is, 2 protons and 2 neutrons, an alpha particle. And so that makes it the nucleus of a helium atom. It's just, that's what helium is 2 protons and 2 neutrons. And if you take all the electrons off of it, you would have an alpha particle. So you need to know this abbreviation, and you need to know that an alpha particle is basically just the nucleus, or its equivalent to a helium nucleus. Okay, so let's write an equation. All right, so for this reaction right here, we have uranium-238, and it's got 92 protons because it's uranium, and it's going to undergo alpha decay. So it's going to spit out an alpha particle. And then what's going to be left over? Well, it's just math at this point. Uranium just lost 4 particles from its mass, right? So what is it going to end up with? It's going to have a mass of 234, because 238 minus 4 is 234. And it just lost two protons right here. So now it's going to be an element with 90 protons instead of 92. And of course, if you were to look that up on your periodic table, you would know that you had a thorium. So in this particular reaction, uranium-238 goes through alpha decay to produce an alpha particle and thorium-234. Okay, so there's some things to remember about alpha decay. Alpha decay usually involves larger radioactive nuclei. I mean, because it's making it smaller in mass and also minimizing the number of protons and neutrons, trying to get down to a smaller nuclei where a 1-to-1 ratio is ideal between protons and neutrons. Another thing to remember is that an alpha particle has a positive 2 charge. I mean, it is, after all, made of 2 protons and 2 neutrons. The neutrons have no charge and the protons have a positive charge each, so nuclear radiation is positively charged, or rather alpha radiation is positively charged. And the last thing to remember is that alpha radiation can be stopped by a sheet of paper. I mean, the reason for that, so that means that alpha particles cannot penetrate paper. And the reason why is because they're big. I mean, they're 4 nuclear particles in size, so they're pretty easy to stop. It's not super harmful. The next type of nuclear decay is called beta decay. In beta decay, a neutron in the nucleus of a radioactive element actually spits a chunk out. So you have a neutron here, and it actually spits out a chunk of itself, a tiny little chunk that carries a negative charge. And then what that does is it leaves behind a positively charged proton. So the neutral neutron gets rid of a bunch of negative charge in this tiny chunk, and then that leaves it positive, so it transforms it into a proton. So you literally get a transformation from a neutron into a proton by spitting out this thing, this tiny little particle. That's called a beta particle. So a beta particle. And you'll notice that a beta particle has 0 mass, it's really tiny, and a -1 charge. So essentially, a beta particle is just an electron. And it's shooting out of there at such high speed, it makes that electron kind of like a little bullet shooting out of the nucleus. So for this example that I gave you, let's write an equation for the beta decay of this cesium-137. So you have cesium-137, of course cesium is number 55 on your periodic table. So it's going to shoot out, sorry, not an alpha particle, a beta particle. And it's so a beta particle is an electron. And its little symbol indicates that it has 0 mass and a -1 charge. So we know that the mass of what's left over isn't going to change, right? So 137 plus 0 will equal 137. And we know that it's going to transform a neutron into a proton. So the atomic number should go up 1 from 55 to 56. And of course, if you do the math here, -1 plus 56 equals 55. So that makes total sense. And then you have to look up what number 56 is on your periodic table, and that's barium. So our cesium turned into a barium by giving up a little tiny piece of one of its neutrons, a beta particle, and it changed that neutron into a proton. So some things to remember about beta decay. The first is that beta decay will increase the number of protons by 1. So you're actually changing the identity of the element because you're increasing the number of protons. But at the same time, you're decreasing the number of neutrons by 1. So the mass of the nucleus actually remains the same. Second thing to remember is that beta decay, or beta radiation, a beta particle, is negatively charged. It's essentially just a high-speed electron. And the third is that beta radiation can be stopped by wood, so something a little more dense than paper, because it is actually really small, especially compared to an alpha particle. Alpha particles are huge, right? 2 protons, 2 neutrons, especially compared to the size of a beta particle, which is just the size of an electron. So let's move on to the last type of nuclear decay. This is called gamma decay. Gamma decay is a little bit different because in the other 2 types of decay, your nucleus actually broke apart and emitted pieces. Whereas in gamma decay, that's not what happens. In gamma decay, the nucleus actually just releases a bunch of energy in the form of gamma photons. And all that really is just really high energy radiation or light. It's stronger than X-rays, more penetrating. It's pretty dangerous, actually. Gamma decay is the one that you have to worry about when you think about like nuclear radiation. It's the worst one. So a gamma, Greek letter gamma looks like this. So sometimes you'll see gamma radiation written, or a gamma particle just written like this, like a gamma. All right, so let's write an equation for the gamma decay of this particular element, plutonium-240. So if I asked you to write the gamma decay, which I may do, so gamma, then what you're going to end up with on the other side is a gamma particle and the same element you started with before, the same isotope. So you might be thinking to yourself, well, what the heck did it go through the radiation for in the first place, or the decay for in the first place? Because it certainly doesn't minimize the number of particles in the nucleus. It doesn't change any of the particles to different particles. All it really does is give off energy. So something that you might want to know, gamma decay is often accompanies the other kinds of decay. So a lot of times with alpha or beta decay, you also get this energy, this high energy light being given off in the form of gamma rays. And also gamma radiation is the most penetrating, meaning it's the worst one. It can travel through a lot of substances. However, it can be stopped by lead, which is why they often line nuclear reactors in lead. They often line nuclear fallout shelters also in lead. Okay, so now we're going to talk about how to write a nuclear equation reaction, or reaction equation, which you've actually already done. So I'm just going to review. So for alpha decay, if I asked you to take this element, radon-222, through an alpha decay and write its products, well, you know it's an alpha decay, so you know it's going to produce an alpha particle. So you need to know that that's the symbol for an alpha particle. And then at this point, it just becomes math, because both sides of the reaction should add up to the same thing. So this 4, when added to whatever this is going to end up being, should equal 222. Or you can take 222 and subtract 4, and you're going to end up getting 218. And then down here, you know that you have 2 down here, so 86 minus 2 would be 84. And then you just have to look up element 84 on your periodic table, and that's polonium. So that's an example of how to write an alpha decay reaction. To write the beta decay, or a beta decay equation, well, you know that you're going to be producing a high energy electron. And again, it just becomes math. So we know that whatever number you have here and whatever number you have here on your product, those have to add up to this number right here. So 0 plus 14 equals 14. And then same thing down here. You have a negative 1, and whatever you add it to down here has to equal 6. So that means this should be a 7. So 7 plus negative 1 equals 6. And then if you look this up on your periodic table, you'll realize that you have nitrogen. And of course, gamma decay is the easiest one. If we have iodine 125, and it undergoes a gamma decay, it is still iodine 125. And then you just put like a gamma particle next to it. All right, so that is all of nuclear reaction types or nuclear decay types. There you go.